Hi, my name is Ashwin, and I've been a fan of Zephyr for a while now, and I thought this was a great opportunity to share our experiences. So, about a little bit about me. I'm at a company called Proto Central Electronics. We are in Bangalore. We sell a lot of these open source hardware devices, especially in the medical field. So, yeah, otherwise called the CEO of the company. But I'm primarily an electronics engineer who also I'm regularly involved in design and also a firmware engineer. At the core, I'm still fascinated by how we code and it controls electrons on a wire. So that's what keeps us going, right? So I've been a Zephyr fan since 1.14.0, which is not too long ago, but it's long enough. So let me just quickly introduce what is open source health devices. First of all, this is open source hardware, all right? So similar to open source software, since we all understand open source software and the concept of Zephyr as well. So this is one part of open source hardware where we take commonly used medical devices and we develop them and we open source the entire design. So what this allows is, there's a bunch of different advantages, which is most of them are self-explanatory. I'm sorry, I'll just start my timer. Most of them are self-explanatory as shown here, but the main thing is that it enables how about now? It's fine. Okay, thanks. So open source and health are always looked at with doubt, because if it's a medical device, if it's important, then why do you want to open source it, right? And are they reliable? But in fact, these systems are more reliable than commercially available systems, because open source in medical is that we do not we manufacture these devices and we also put these designs, right? So anyone can audit a system. In fact, since everything is there, so you can audit a system. So, and we've made some baseline design decisions, right? So some basic safety guidelines and everything. So we do not take care of the local regulations. Our customers take care of the local regulations. So who are our customers? Customers are mostly researchers, medical device developers, and scientists working on health data and things like that. So since we've already set a baseline safety consideration, it's easier for them to go through the regulatory process, which is local to every country. And the last one is also very important. You make a device work on your terms rather than the other things. You don't have to learn how to use the device. Instead, you make a device that works for you. So, our first project, I would just try to introduce something very simple that all of us know. It's a vital signs monitor. It monitors all your vital signs and usually reminds you of your time in the hospital, right? So in the beginning, this is how we started with open source health. This was in 2017. We made a completely open source vital signs monitor. What is open source in this is, it's designed as a hat. Hat is an add-on board for a Raspberry Pi, and it has ECG, respiration, SpO2, temperature, and it was using a SAMD21 from Atmel to capture the signals and send it over to a Raspberry Pi. So what you see here is a standard Raspberry Pi display, and this whiteboard is the one that sits on top of it and captures the signals, sends it to the Raspberry Pi for processing, and displays it. we won if anybody has heard about Hackaday, we won a 2017 Hackaday prize for this. Made this primarily as a tool for medical research and development, and also a reference design for resource constrained settings, right? So this can be manufactured anywhere since all the designs are available. And they don't have to be scary. This is one version that we made, where this is my little nephew who's 2 years old. He asked, what is SpO2? Right? So that yellow line is actually the SpO2. We made a rabbit jumping over it, and he understood what SpO2 was. It goes up and down, and if it doesn't, something is wrong. But are these open source health devices actually practical? Yes, I do think so. Because since they have there's a lot of doubt about it. I wanted to get this clear. So there is an association known as the Open Source Hardware Association. It's a bunch of open source companies that get together, and we are also a part of the association. They recently received an a US NSF grant, asking them to research whether they call it open healthware, is actually feasible. I'm also part of that study. And POSE stands for some open source exploratory, something like that. So yeah, you can read more about it on the OSHWA website. So let me talk about our products. I'm not here to advertise our products, but since these are all open source, I can easily talk about them without worrying about disclosing anything sensitive. So 2017 was the revision 3, that is the first version of the Raspberry Pi. Although it's called revision 3, it was actually revision 1 because the previous ones failed. So this was the first commercial one. So that's the one that I showed you earlier, based on the SAM D21. Revision 4 came in 2019 with it was based on a single ESP32. It added Wi-Fi, Bluetooth support, and we also made an open source mobile app for Android. Revision 5 was in 2023, 2 years ago, and that was based on in between you can see COVID-19. So that is where we ran into issues, right? All the previous components that we had used in the board were not available anymore. Some from TI, actually. TI ADS 1292 is ADC that we used that went out of stock. And when we asked TI, they said, we don't know. So we had to quickly change everything, right? So it took us a few years, but this time we had 2 processors. One was an RP2040 from Raspberry Pi. Although it's from Raspberry Pi, it's quite a powerful chip that you can check out. Or the latest version of it, the 2350. And an ESP32 for wireless. And yeah, it had data logging, it's got an onboard flash and everything. And the latest version is wearable. It's called the HealthyPi Move. So we just call it HealthyPi, and because it's mobile, it's Move, which is the one that I'm wearing here. So it's like a completely open source wearable smartwatch. Now this is based completely on Zephyr. It runs on the NRF5340, a single chip, but it's got 2 cores. One is a network core, one is M33 core. So I'll go into more detail about how we developed the Move alone, because can't go into too much detail about the rest because of time. So how do we get it funded? You want to go try asking a venture capitalist for funding for an open source device? No. So we didn't even try that, right? So we didn't get funding that way. So we did crowdfunding. I don't know if you guys have heard about Crowd Supply. It's kind of like Kickstarter, but it's for mainly for open source hardware. So we ran 4 campaigns, and Move is the latest one. We just ended, and we just supplied our first batch of devices. So where does Zephyr fit into all this, right? Till now I just spoke about the devices. So before Zephyr, let me go into that first. So I'm going to start with where we used NRF 52840, that is the one from Nordic, for one of our commercial products. Like, we have another company where we do make medical commercial products, and we're not very good at that, but because regulatory stuff is a huge burden. Right? So I still love what I'm doing. So NRF 5 is where, I'll tell you where NRF 5 bridged the gap, but there was all these SDKs, right? And FreeRTOS, we don't even know what that was doing there, because it's not actually an SDK, it's just a framework, right? And Arduino, of course. So we had Atmel, STM32, Raspberry Pi, and all this. So this saying, actually I copied from somewhere and I changed it according to a developer. A coder walks an arrow trail, because each driver is handmade, and each feature is alone in the forest. So what do we do? And the picture on the right, that is also very important, because that is how you used to configure the Nordic NRF 5 SDK, which was, to put it lightly, quite horrible. And I've told this to the Nordic guys, so I hope nobody's from Nordic here today. Yeah, I've shared this with the Nordic people already. So, but I guess Nordic realized that they were bad at software. So they decided to go from NRF 5 SDK to NRF Connect. NRF Connect, as far as I know, Nordic was the first company that took their primary SDK to Zephyr. NRF Connect was their primary SDK, and it was completely written on Zephyr. It was a downstream fork of Zephyr, and it had their own libraries on top of it. And this really opened our eyes, right? This really opened our eyes, saying that, okay, this was something great. Even from the architecture, I'm not going to read out what is on the slide, but you get the idea. So then, I had an image there. I guess that didn't come, but so Zen, right? So there was an image of a monk attaining Zen at this point. So Zen and the art of firmware evolution. So the reason why I put this thing is that once we realized that, so these are the basic changes that what we, from our perspective, we saw. So control, simplicity, portability, and I just added the Bluetooth stack because that was one of the main components. So I don't know how many of you have worked with Nordic devices, but they had this stack called Soft Device, which was not good. And it was very difficult to tune parameters and all that. So then came NRF SDK, and then now we are with. So anyway, I'll go through the next process how we did that. I'm sorry. Yeah. The last one is the mainstream Zephyr. Yeah. That's why you would see a lot of NRF developers in the Zephyr community, because they invest a lot of their time in Zephyr. And Zephyr is currently their only supported SDK. So then we thought, okay. So then we had all these devices, right? So we had a HealthyPi 5 based on RP2040, and then the Move is the recent one. I left out some devices in between, but all of these are unified by Zephyr. So which means that we have one code base, basically one repository, and each device is basically a fork of that repository, right? So most of the Zephyr device drivers were the same. Libraries like LVGL, this runs LVGL. I will talk more about the libraries also. I don't want to take too much time. So HealthyPi 5, HealthyPi Move was based on NRF, and HealthyPi 6, which is in development, it's based on an STM32. And we have some future versions also planned. So we have the code base, we have Zephyr drivers, which are the ones in green are stay exactly the same. Algorithms and signal processing are packaged as libraries. I'll just describe what I mean by libraries. And then we have platform specific overlays. So these are DTS overlays, kconfig overlays, and different CMake files. So this is based on the available data sources. Each one can have different types of sensors, but basically the sensors that capture the same data. So HealthyPi 5 had, for example, an SpO2 sensor based on TI, AFE4490. And the HealthyPi 6 has one based on Maxim. So the data which comes out of the sensor is the same, which is PPG, but the driver is different. So our bottom layers remain the same. And different storage modes, screen size, of course. All of them are based on LVGL. For this one, we had to work with a really small screen, but it's pretty high resolution also. So let me just quickly go into how we did this, and taking our latest project as an example. Now I'm taking all this as examples because I can. There's nothing to hide here. So I developed experience with this HealthyPi Move. Right? So it's a wrist wearable device, which is a fancy way of saying smartwatch. But it is not a smartwatch. It doesn't have any smartwatch functions like calls and stuff that is there in any other watch. So we don't want to do that. Instead, it's same as a HealthyPi that we started with earlier, which is still a vital signs monitor, but on your wrist. It's a single NRF 5340, but here we had a 390 into 390 pretty high resolution full color OLED display. Now this was a challenge because on one processor, and we had flash, and these are the parameters. This is completely open sourced. Everything is open sourced, even the enclosure and the strap design, if anybody wants to make that. So how did we migrate from NRF Connect to mainstream Zephyr, right? So NRF Connect, so we got used to NRF Connect so much that we were using most of one of the core parts of the Nordic SDK was the common application framework. It's just a bunch of layers which act like an event management system. So the Zephyr equivalent of that was, these SMF and ZBus came in the recent versions of Zephyr, quite recent, I think 3.7. But we were able to quickly migrate everything to SMF and ZBus. So what event management does is, so there is one Zephyr bus. So for stuff that you don't need to create a queue for, a message queue, you use ZBus to push data to different modules. So it's kind of like a message bus, and there are different channels. So I didn't want to put any code here, but just because I wanted to show the simplicity of Zephyr, I wanted to put the code here. Now, it's okay if you cannot read it clearly, but so a basic implementation of ZBus will be channel definitions. These are your channels. So here we have a heart rate channel and an ECG timer. I'm not going to go into what they do, but they have to publish this data on a regular basis. So a heart rate channel, and then there are listeners. Listeners are there in different modules. So for example, we had one listener. The first one is the display listener. So display listener is on the display module. It takes the data from the heart rate and puts it on the screen. Similarly, we have a Bluetooth listener which takes the same data. Now this channel can go to different listeners, right? And then once you connect this, you just have to publish updates. It's just one line. So no queues, no setup necessary. And the memory for this, it's not dynamic. It is from the system work queue. So it's safe. Similarly, state management. So we have a state machine, like a regular state machine that you've seen in software engineering, transitions from state to state. So here we had a state machine for when the display goes to sleep, when it wakes up, and deep sleep, all that stuff. So we have different states. We have one thread which runs the state machine, and we define transitions between states. For example, if I touch, it wakes up, that's an event, and it switches the state. Device drivers. Again, this is the device driver model taken from the Zephyr project website. It's not very clear, but now I don't want to go into the details of this, but there are two ways to read sensors. The reason I put it here is because this fetch and get was the older way to read. It is still the main way, and there is read and decode. Read and decode is so these are just two ways of reading sensors. I'm just putting it on a higher level. So basically, what it does is fetch fetches all the data from a sensor, stores it, and gets the data from the sensor's buffer to the application. Read is a direct stream of read, and then the application decodes it. I'm keeping time. So again, we used read and decode only because I'm totally against the fetch and get thing, because most of these sensors that we have are high-speed sensors, right? So fetch and get, I think they were designed with a specific set of sensors in mind. Like everybody talks about an accelerometer, and that didn't really work for us. We wanted access to the raw sensor data. And in fetch and get, you'll have to make sure that every sensor value is encoded into that sensor channel structure, which doesn't really make sense for a lot of things. And here we get the raw data and then we decode it. Again, I think I don't want to bore you with this, but if people have used Zephyr for doing an RT real-time I/O application, then that's what this shows. You submit a request for an RT I/O. It can either be a blocking request or it can be callback based. And in the app, now this is somewhere that we've stepped away from Zephyr standards, because you're supposed to decode that, provide a decode function, but instead we decode it in the app. If anybody is interested, I can explain later. And portability. So this is the main reason, right? So whenever we develop a driver for a particular device, and we are not ready yet to push it directly to the Zephyr repository, because we want to make sure that all the coding standards are followed. So instead, what we do is we maintain a separate repository, this is for a MAX 3001 ECG sensor. So we have a repository. So you just add that repository's URL to your West manifest. You enable the driver in your conf file, add the device to an overlay, and your device is ready to use. It really is that simple. I mean, if anybody would want to use it like this, it's and the reason why we did this is because we needed the same driver across all our platforms. The MAX 3001 we used on our first device, HealthyPi 5 and HealthyPi Move, and the new 6. Similarly with libraries, we had one firmware updater library. This is not MCU boot, but this is a firmware updater for a chip that already has a firmware inside the board. I mean, the main processor takes the firmware and updates the firmware of the other sensor. So we wrote it. It can be used for different things. So we created a repository. It's public. I mean, all this you can find under GitHub Proto Central. So coming back to this, right? So using these portability things, that's how we achieved this kind of an architecture across platforms. So other great features that we constantly use are code relocation. I'm just saying why Zephyr makes things much easier. I come from an MCU background. I've also worked on Linux kernels, but that was a long time back. But I think you were mentioning in the morning about where they come from. Yes, that does matter. There was a sharper learning curve for this, yes. But in the end, it seemed to just make sense. For example, code relocation. Whether it was for putting a piece of code in Flash for execute in place or putting it in SDRAM, it was simple. The little FS file system which came with this works great. MCU boot. Then there is security. All the crypto functions that are required comes with Zephyr, and they work on mostly every platform. I mean, we've used so far these libraries, all of these libraries, on most of the things are ARM platforms, whether it is an M4, M3, or M33. But some are all the ESP32C3 is also RISC-V, so it works on RISC-V also. And this is the product in development. This is the HealthyPi 6. You can see that this is now a totally different beast because it's got an STM32H7, which in turn has two processors. It's not a dual core processor, it's two different cores. It's an M7 core and an M4 core. So we're using the M4 to do sampling at high speeds and the M7 to handle displays and other things. Wireless, again, offloaded to a different thing. Earlier we had 512 KB of RAM for this device. Now that became 32 MB flash, and we used a 5-inch MIPI DSI display, which was full HD. And I mean, the experience that we had porting our HealthyPi original code base based on RP2040 to a totally different system, which used external RAM, external flash, a 5-inch full HD display and everything. It was effortless. I mean, it just, I mean, of course, the core, the SoC support for H747 is available. So we just added 757, which is also a variation of that. And the sensors are different. This has got a 5-channel ECG, so that's based on ADS1294, again TI. 32664 we loved it, so we used it here also. And this one is extensible. You can connect any number of sensors through I2C and daisy chain them also. So this is still under development, so we hope to complete it in the next 1 month. So conclusions. So one thing that I remembered is that Arduino removed the fear of coding in a lot of people, fear of starting coding. Zephyr removes the fear of scaling. I mean, now this doesn't, whether I just showed you the example of how from a small processor to a large processor, most of the things remain the same. And right now we don't have any vendor lock-in at all. Earlier we used to be stuck with Atmel and their Atmel Studio and all that. and then Nordic. Now, HealthyPi 6 came up 3 months ago. We were thinking which processor to use. STM32H is not something that we used before, but we had no hesitation because we know that Zephyr would support it. So any processor that comes along, we are ready to handle them. And you decide which features you want to implement. You don't have to do everything, right? So, I mean, a lot of people compare FreeRTOS to Zephyr, but that comparison is wrong because FreeRTOS is just I would say it's just a scheduler with some OS support. Zephyr is an ecosystem. Right? It's not just a RTOS. It is a bunch of different things, different modules, different drivers, different community, and the services that Zephyr provides, I've not seen before. And we used to use a FreeRTOS a long time back, but so initially I also had the hesitation of why switch to Zephyr, which when I looked at the architecture was quite fat. Why put such a fat system in a microcontroller? But then I learned why. It's really not fat. Just the architecture is. Yeah. Yeah. So here, one thing I've put here is that when I was configuring, I wanted to put this thing called, okay, that one is monolithic and that one is modular, but it is not actually. But because the output is monolithic, it's just Zephyr generates one single binary, so which is still small, which is quite small. So although the code base might be quite big, the output binary that is generated is smaller than any other OS that I've seen. So that's it. Any other questions? Huh. So drivers for devices like, for example, ADS 1292, we wrote the driver in the Zephyr format. We did not just take a driver and translate it. We just took the driver. We just wrote a driver. And driving... yeah. So ST... so Nordic and ST have a lot of Nordic support for their SOCs. I'm not talking about the other drivers, the peripheral drivers, but for their SOCs, they provide full support. And similarly, other companies also. I'm not sure about TI because we've not used it yet, but STM32, Nordic, even Espressif, that support is not so much because they still have a lot of binary blobs in them. So you'll still have to download a lot of blobs. But other things like Raspberry Pi 2040 was completely community driven. That the support given by the Raspberry Pi Foundation was only a C++ SDK, and the HA layer for Zephyr was completely community driven from scratch. And in fact, the recent chip that they launched, the RP2350, which is the successor to the older one, that is also completely, I also contributed a little bit to that. So that was completely community driven. So, but some things remain the same, right? For example, both use the Cortex-M core. So at least the SoC and the core level things remain the same. So the beauty of Zephyr is that you can define an SoC. That's what we did for STM32, this version, H757. It was not there in the list when we saw. So we just made a list of what all it has. There was 747 support, where it had that also has a Cortex M7 and M4. So we just took the same thing, added some extra pins, and MIPI DSI support was there in some other STM32. So we pulled that up, put it together, and that's how we made an SoC definition. So there's a lot of reusability here. Any other questions? So if anybody wants to see this device, I have it one here. So you can just catch me around somewhere and you can wear. I mean, if you'd like to wear, you can wear. Don't worry, it won't bite. That was called ZS Watch. Yeah, we've met that guy. He's from Sweden, and but we do not support smartwatch functions here. Same as how they don't support health functions. They just have a PPG sensor from a ready-made thing. So we do not have call notifications or anything like that. So that is why here I mentioned that loadable modules, LLX, is something that we're exploring, and we have had some level of success. So if people really want to bring call notification support or whatever it is, they can make them as linked time loadable modules and then load it into the flash. And when the app is loaded, when you swipe the screen, then you go load that particular app. So yeah, it's kind of like a user space app. It's exactly like a user space app. But user space and kernel space is not really so tightly defined like in Linux. But yeah, there is core protection and everything. So the root of trust, especially if you're using a device like NRF5340, which has the TFM support, then there is some protection and all that. But that's the limit of my security. Those are libraries that we made, and we have made it open source, so that we can use them across projects. And now we support a lot of other frameworks and stuff like that. Now other customers have also started asking for like Arduino drivers. Do you have Zephyr drivers? So we provide Zephyr drivers also. So the algorithms are. Some use. I think there is an initiative inside the Zephyr project for a DSP library, but I'm not following that very closely. Something based on CMSIs, but it's Zephyr specific. I don't know the status. Okay. Next